Hi and hello everyone. For today's lecture, we're going to have a forward difference approximation. So forward difference approximation is used to approximate differentiation or derivative. So I'm gonna show you the formula for forward difference approximation. So it is just you want to find the derivative for f for the function or f prime x. So this one is going to be fx plus h minus fx divided by h. So this is the formula for forward difference approximation, where h is the step size. Okay, see, I'm going to show you how to use this formula for this one example. So let's say we have example here. Estimate, I'm sorry, my handwriting is so terrible. Estimate the first derivative of this function here, fx equal to 0.15x cubed minus 0.5x plus 1.2 at x equal to 0.5 using step size h equal to 0.5 and h equal to 0.25. Now let's start. Let's solve this. So now you have your function here, and you have the x and also the h here. So we have two value of h. Let's say we start with h equal to, okay, different color. Let's say we start with h equal to 0.5 at x equal to 0.5. All right. So now you need to know that your x plus h is equal to 0.5 plus 0.5. So that is 1.0. So why we want to find x plus h? Because remember that we have this formula here. Oh, sorry. Remember that we have this formula here. So this is the one that we need to find out. So we need to find out fx plus h. So for this example, since our x plus h is 1.0, so we need to evaluate function at 1.0. Okay, so with this, we will have, okay, just simply plug into the function that we have in here. Okay, the one that we want to find the derivative. So you just plug in. So you will have 0.15 minus multiply with 1.0 to the power of 3 minus 0.5 multiplied by 1.0 plus 1.2. So that will give you 0.85. Now what's next? What's next is you need to find out. So you already have this. Now you need to evaluate the function at x equal to 0.5. So next is fx. So that is x is equal to 0.5. So just plug into the formula. Just plug into the equations here. So that's going to be 0.15 multiplied by 0.5 to the power of 3 minus 0.5 multiplied by 0.5 plus 1.2. So you will get 0.9685. Okay. So next is you plug into the formula. So we are trying to find the f prime at x equal to 0.5, or first derivative of the function, using forward difference approximation. So simply plug in the value that you already calculate. So you will get, this is H, which is 0.5 at the moment. So this one you will get 0.85 minus 0.96875 divided by 0.5. So that will give you minus 0.2375. So this is the approximation for the first derivative for this function. Now, you cannot stop until that. You need to carry on, in which you need to find out what is the percentage relative error. So the formula for percentage relative error is true value minus approximation value divided by true value. Now, before we want to proceed with this, so we need to find out what is the true value. So the true value for this function is, because okay, I'm going to show you this. Fx is 0.15x to the power of 3 minus 0.5x plus 1.2. So you are using calculus to get the exact value for the derivative. So that is f prime x. So 3 times 0.15, so you will get 0.45 x to the power of 2 minus 0.5. So here, simply plug in 0.5 in here. So you will get minus 0.3875. So your true value is minus 0.3875. So you're going to plug in into the formula here. So the true value using the calculus, so you will get minus 0.3875 minus approximation value is this one, so minus 0.2375 divided by minus 0.3875 in here. Okay, I forgot you need to have this one times 100%. So this one is times 100%. So you will get 38.71%. Okay, so using step size h equal to 0.5, you will obtain the approximation for the first derivative as this one with 38.71% relative error. Okay, so let's carry on with h equal to, let's have another color. So let's carry on with still the same x value 0.5, but a smaller step size, which is h equal to 0.25. Because remember, the question here asks you to use h 0.5 and h 0.25. Yeah, so x plus h, so 0.5 plus 0.25, this time around it will give you 0.75. Next is you need to evaluate fx plus h, so that will give you f, so this time around it is 0.75. So you just simply plug in into the formula there, sorry, not the formula, the equations, the function. So it's going to give you 0.15, 0.75 to the power of 3 minus 0.5. Then that is 0.75 plus 1.2. So that will give you 0.888281. So that is only the value for the function when you add up x with the h. Next is you need to find out the fx. So fx here is 0.5, and we have obtained this previously, and this is 0.96875. Therefore, Therefore, your first derivative for x equal to 0.5 is approximately, for this h equal to 0.25, so it's going to be f 0.75 minus f 0.5 divided by 0.25. So that will give you 0.888281 minus 0.96875 divided by 0.25, and at the end you will get minus 0.32188. So this is the approximation value for first derivative of this function. Now you need to carry on with the percentage relative error. So with this, you need to plug in the value of the true value minus approximation value divided by true value times 100%. So that will give you minus 0.3875 minus 0.32188 divided by minus 0.3875 times 100%. Therefore, you will get 16.93%. Now, looking at this, when you compare with h equal to 0.25, you have smaller relative error compared to this one. So this one is better. Yep. So we will take the value. We prefer this value. Yeah, because we prefer this function with h equal to 0.25 because it gives you smaller relative error. That's it.